Good morning, mathematicians. I must be losing it. Because yesterday I was being so stupid on live stream. I was being so goddamn stupid. Oh, maybe I shouldn't have said that right at the beginning of the stream. I have no idea how demonetization works or what I'm allowed to say and not allowed to say without losing my money entirely. Also, my setup's a little different today, so I don't know if I need to talk as close to the mic. Okay. But let me tell you about the silly thing I did on stream yesterday. Obviously, the question that someone asked about algebraic geometry makes sense. Right? I mean, they were asking about a polynomial map, right? They were asking about the map from A1 to A1. Somehow I said it didn't make sense, but obviously this is a polynomial in like coordinate functions. You know what I mean? Like, of course you can square it. I don't know what I was thinking. Maybe to keep track of things, we'll call this X and we'll call this Y. And yeah, so the corresponding polynomial rings, kx and k big Y, so I'll use like little variables like this, I guess. Yeah, the point is the map, you get a map going in the other direction that comes from F. But it's not what I said it is. It's just pre-composition with F. So it'll just send a polynomial to pre-composition with F. Of course. So, in other words, the question is really about this module homomorphism, or this ring homomorphism, sending a polynomial py to p of x squared. Yeah, well, the fun thing today is realizing I was a complete idiot in yesterday's stream when it came to the algebraic geometry question, which somehow I landed at the conclusion that it didn't make sense, but obviously it makes sense. But now actually I forget what they were asking me. I forget what they asked me to show about this map. So I was just trying to sort out details about the map. I can't remember what they wanted to know, if this map was yeah. I guess we can go to my own video and see. Unless there are other questions. Unless there are other questions. Oh. Yeah, I guess we'll float through and try and find this person's question. Oh, is it a flat morphism? That's what they're asking. Okay, great. Okay, great. So, is it a flat morphism? So, well, that's the same as asking basically kx, um, kx is gets turned into a ky module under this action. So in particular under the action of py, acting on px. Oh, hello, Desin. That is a great way of saying hello. That's fantastic. Okay. So of course, py is going to act on qx by px squared qy. And we want to see if this module, so I guess it doesn't really matter, everything's commutative, but maybe I'll tensor on this side. We want to see if this is a flat module. And it would certainly be flat if it were free. The question is it free? Is it a free ky module? No, I don't think so. I don't think so. What could we do? I guess we could try computing. Do we really need to go and compute a resolution? I wonder if we can just do it directly. Like suppose we have a sequence of k modules. Intuitively, there should be something happening at the origin. Right, because I guess, yeah, but I think the thing happening at the origin should come from ramification, right? Because basically it's like we've got it'll be something like this, right? Let me draw a better picture. I mean, here's our copy of A1 below, and here's our copy of A1 above. And it's like we've got this the fiber above most points has two things, but then hi Julie, but then the fiber above the origin is just going to be this like multiplicity 2 point, but that's more an artifact of ramification. Why is it called flat? That's a very good question. Why are flat morphisms called flat? Or, I mean, why are flat modules even called, yeah, I don't know. That's not a very convincing explanation. Why are flat modules called that? Okay, let's see what AI looks like. Essentially, a module is flat if taking the tensor product. Yes, I know the definition. It means it flattens the structure of the sequence. I guess. Yeah, I don't know if there's a better explanation. I think that's it. So, I mean, we could check flatness by checking local flatness, right? We could localize this if we wanted. Um, and yeah, I don't think the flatness will manifest locally here, right? Because, I mean, this module, well, maybe it could. Um, you could try localizing at every prime, I guess. We need to localize at all the primes. And I think maybe we can assume algebraically closed. The viewer, the person who posed the question, I think, did say they were happy to assume algebraically closed. So then, what do we do? I guess we're localizing. We could check the localization of kx at every prime ideal of ky, right? Well, it's not so clear that helps though. I was thinking maybe flatness would pop out or something. Hello. I don't know. I'm not sure the right way to pronounce your name though. Messaged. I'm glad you could make it to the stream. Away from the origin, it's definitely free. It's just a sum of 2 copies. Right. Wait, is it free? Because I guess, what do we have? We have 1. Right, because I guess it's I was worried there was going to be relations or something. No, but I guess you're right, because like I guess we have 1 and x as a basis, right? And then right, so then we can definitely wait, is it free? Oh, I guess sorry, right. I guess we need the whole free but of countably infinite dimension. No, that's not true because the scalars come from ky. So we can write everything right as a polynomial. Right. Okay. Yeah. 1 and x will be the basis. And you put any polynomial here, px squared, qx squared. We should get any polynomial out of that, right? The only thing I'm worried about with the freeness though is that like there's maybe a non-trivial linear combination here, right? Like if you took px equals x, and you took qx equals 1, then you have px dot 1 plus qx dot x would be x squared plus 1. Maybe that's another problem. But you see what I mean? I feel like there's something going on there. Wait, yeah. How could I cook this up to be problematic? Maybe I can't. Maybe no. Yeah, maybe it's not an issue. Interesting. Okay. Away from the origin, but yeah, I guess I don't see. I mean, I've been arguing this sort of at a global case. I don't see where the origin problem comes up. Let's just look at examples of flat morphisms. Let's see. This interesting. That's flat. Computing the Tor group. Yeah, maybe do we need to compute Tor? Is that it? Maybe that's the best thing to do. That shouldn't be so bad in this case, right? But it does seem flat, right? I mean, if this really is free at the global level, then it's a flat morphism, done and done, right? I'm thinking. I kind of want to change the locations. It was noisy in my living room before, which is why I started the stream here. But I want to head back over there. So you're all going to have to bear with me for a moment. I don't know. Think of more good questions to ask me while I'm transporting stream through my house. I guess you'll get a tour. You'll get a mini tour of where I live. I was planning, 6K sub, my house reveal. But I guess Christmas comes early. Okay, I'm gonna need you all to entertain yourselves for like 30 seconds. I know it's supposed to be my job, but I'm slacking off. Okay. Hope you all survived. Hello, Fimnal. Where is the guitar section I promised? It's happening right now. I forgot to do it last time. Let me just get myself together here. Make sure let's make sure. Nope, didn't want to go there. Man, does anyone else hate Teams? Can I get some hate for Microsoft Teams in the chat? Just gonna make sure things are framed nice and pretty so you can see my plants and my guitars. Okay. I wish I remembered my basic algebraic geometry. I can't seem to prove something's flat on stream. Hodgson would be so disappointed in me, 'cause I can't prove things about flatness on my stream. There you go, daily guitar section. Daily guitar section. Yeah. New album Math album dropping probably never. Um, Sarah introduced the term flatness and was asked why in an interview, and he said he doesn't remember. Hell yeah. Hell yeah. I love that. That is a good piece of lore. And it was probably arbitrary and certainly doesn't have a geometric reason. Amazing. That is amazing. Is this interview available somewhere? Is this like on YouTube or something? Um, uh, hate them, hate teams, yeah, hate teams, yeah. Hate teams, MATLAB and Excel. Hmm. Yeah, don't love MATLAB. Have been coming around to Excel, but for the sole reason why, for the sole purpose of like before my workouts, I would like track how much I lifted just on like a notepad app, and then also for like calories and protein, I was tracking that on like a built um, an app specifically designed for it, and then I don't know, it just kind of went downhill and it started sucking. And then I realized that I can just use Excel on my phone, um, and set up like the sum function to like have it track like my total calories and everything. And now it's awesome. Now I use Excel to track my weight, my calories, my lifts, my protein intake, and yeah, it's great. I don't know. I don't know. So I'm coming around to Excel, to be honest. But I don't have to, I just use it for very easy bookkeeping. I don't have to use it. Wow. Wow, we've got some serious slander in chat here. Microsoft Teams is the stats of math. Wow. If I was a younger man, if I was still in my undergrad, I would have said that. Tomorrow you have an exam, which, if you get, you can get into a better undergrad college. Nice. Nice. Well, good luck on that. You just opened YouTube for your stream and my guitar. Good. Well, hopefully the music will move you to have good thoughts on your exam. Quandle is just an arbitrary nonsense word. I mean, most words are. But what the hell is quandle? An algebraic structure similar to a group, but inspired from Riedmeister moves. Interesting. Racks and quandles. Yeah, that is super nonsense. You've been studying math for 4 years, and you still haven't seen quaternions show up anywhere. Do I have any cool results about quaternions, quaternionic algebras, quaternionic schemes, manifolds, etc.? Well, yeah, there's a bunch of cool things. Oh, hey, my writing pad acting up. There we go. Also, quaternionic is the coolest word in math. It's pretty good. It's pretty good. Would I definitely say it's number one? I don't know. Symplectomorphism is pretty good. Like, there's a debate to be had there, at least, at the very least. There's a debate to be had. Algebras are way more interesting. The algebra words are way more interesting than in analysis, where most things are named after people. Yeah, I could believe that. Although, I mean, symplectomorphism, where do you put that? It's very borderlands of analysis and algebra. Uh, Nuclear space, paranormal space, yeah. Yeah, cool and dumb. Yeah, kind of like me. Cool and dumb. Kind of like me. Quaternionic sounds like some sci-fi nonsense. Yeah, that's true. That's true. So, I mean, one place where quaternions show up, uh, one place where they show up in a useful, well, they give rise to the hop fibration. So I don't remember exactly how the map goes, but there's some way that you use the quaternions because the unit quaternions. I mean, this gives you the sphere S3, right? Oh wait, am I? Yeah, 4 coordinates. Yeah. So that gives us the sphere S3, and then so there's some way that you use like the nice multiplication rules of the quaternions to define uh, the a structure, the hop fibration. So that's one thing that's really cool. Quaternionic. Okay, importance of symplectic group. One thing I should do is I should write things down. Because I notice sometimes I forget things that people ask in stream. So I'll come back to the symplectic group in a moment. That's because analysis was a French field, and algebraic terms are mostly derived from German, hence sound very cool. Das ist richtig. Ja. Nuclear space is from functional analysis, so it contradicts the whole analysis doesn't have cool terms. Yeah, but I mean, functional analysis is the algebra of analysis. Almost forgot about the Lie group structure on S3. Me too. Sn doesn't have any Lie group structure unless n is 0, 1, or 3. Yeah, I could believe that. I could definitely believe that. Oh, interesting. Nice suggestion, Julie. Yeah, quaternion multiplication is used to construct Milner's exotic 7 spheres. I actually didn't know that. That's very cool. Another place they come up as well is so like in my work, well, we want to study like algebraic groups or something, right? So this may be something I'll talk about more on stream. And actually, I mean, by the way, why do symplectic groups come up? One of the reasons is like, let's say you just care about the, I don't know, normal groups like these ones, and you start studying them. But you're very naturally led to the notion of simple groups, and you're very naturally led to the notion of root systems and the correspondence between root systems, and well, more directly to Lie algebras, but then also to the groups. So, okay, that's just a very quick explanation. So you do all of this, and then you look at you classify this in terms of root systems, and you realize, oh yeah, like all the root systems can actually give rise to a Lie algebra. And so you carry out the classification of simple Lie algebras in terms of root systems. And then you find that there is one that just corresponds to the symplectic group, right? So it's almost like just by asking the question, what simple Lie groups are out there, you're sort of forced into the study of this. Okay, but actually there's so much more to say about it. It comes up in physics and math and like theoretical math and all of these places. Very important. But right. So what else was I going to say? Oh yeah. So but we have this existence theorem, right? And we also have a uniqueness theorem, which says that like for all of our root systems, phi over an algebraically closed field, I can cook up a unique, up to isomorphism, a unique group corresponding to that root system. And so, wow, there's a lot of questions in chat. I'm going to try and finish this thought first. But then maybe you don't want to work over an algebraically closed field. What if you want to work over the real numbers or QP? And so it might be the case that you have, say, two groups, say, over QP, in my case, which are not isomorphic over QP, but they do become isomorphic. They correspond to the same root system when you go over QP. So somehow these groups should be related to each other, right? And we call these are forms. And this doesn't just apply to groups. You can also like talk about the same sort of thing with varieties, but okay, there isn't the root system connection, which I wanted to pass through. So what? What am I trying to say here? And actually, this is an important idea in my work. Sort of, you write down the original geometric version of like the p-adic local Langlands program, or even the real case, and it was the idea of Vogel, or maybe I guess if it goes back to real groups, maybe it's the idea of Adams, Barbash, and Vogel, that I talked on the stream before that there was some. I promise this is something to do with Quaternions, and I'm telling you more than I need to. There's some correspondence between representations and perverse sheaves on some variety, and if you just take the sort of naive setup, yeah, you find that all of the representations correspond to sheaves, but somehow you get more sheaves than you bargained for. And is the idea of Vogel / Adams Barbash Vogel that instead of just considering representations of one group, certain special forms of your other group show up, and then in order to get the bijection, you need to simultaneously consider the representations of those other groups. So now normally you just work with pure inner forms. So actually that, I don't know why I talked about this, because that part doesn't enter into what I'm about to say. But all of this yapping is to say that, so I think it's the case, if I'm not mistaken, I think it's the case that for, at least certainly for GLN, one of the forms, it's not a pure inner form, but it's still I think like an inner form. And we're studying is you basically let D be like a p-adic quaternion algebra, and then you consider GLN over D. And then the representation theory is like very similar to GLN, but it's like this interesting other form. Okay, that was I did not have to make that explanation as long as I did. That was not was really not worthwhile. And there's probably way more things I could have said more simply about Quaternions. But oh well, this is my stream. I'll yap needlessly about my research if I want to. If you don't like it, you can go prove a theorem. How about that? Why is SN, or N is even, harder to study? Is it true? Is that true? Is it harder to study? I don't know if that's true. Maybe. I don't know if the book is translated into English, but there's a book called Zahlen, Numbers, by Ebbinghaus. And he covers a lot of nice things related to, of course, numbers, and among them quaternions. Okay, good to know. Good to know. Isn't there also an easy way of showing that SO3 and RP3 are homeomorphic using quaternions? Really? Yeah, probably, because there might be. Although, do you even really need quaternions? Because I guess, you somehow make some identification, like you have O3 acting on S3, right? And then how do you get how do you get RP3 is you just take the antipodal quotient, and then that that should somehow correspond to taking the determinant 1 quotient here. So yeah, maybe, but I don't even know if you really need quaternions. Supposing that's true. An advisor, in quotation marks, of yours said that every math student should own this book. Oh, the Quaternion book? Maybe. Everyone should own the books that I think are the best. That's what's true. Fun fact, there are pairs of real reductive Lie algebras such that G is maximal in H, but the complexification of G is not maximal in the complexification of H. I could believe it. Yeah. One thing I would really like to, in terms of finding smooth structures, maybe. I mean, maybe one thing, because I know, there's questions about like, even dimensional spheres, having complex structure. And like, if you're odd dimensional, then you definitely don't have complex structure, right? If you're odd real dimensional, you definitely don't have complex structure. So just more interesting things can happen in even dimensions, I guess. One thing I'd really like to understand better is like there's some way to read off from the Dinkin diagrams like all your real forms. Like I've looked it up a couple times, but there's some way it's like, oh, you fill in 2 dots and then like this has to correspond to the compact form or something. I don't know. Does anyone know about this? It'd be nice to really. I wish I had a tutor that just knew this, that I could pay for a session to just teach me real forms via Dinkin diagrams. Satake diagrams? Yeah, I think that's what they are. Yeah. I've only looked at this briefly, but it'd be nice to learn this more properly at some point. Math is such a great pyramid scheme. I would pay someone money to hold my hand through some of this, even though it's probably not hard. I don't know. I looked over. I just couldn't find like a good clear resource that had a bunch of like smooth brain baby examples. But yeah. But the great thing about the math pyramid scheme, right? I would give someone money to help teach me this, and hopefully more people will give me money to teach them stuff, and then hopefully those people who are giving me money to teach them stuff, are going on to like charge high schoolers money to teach them stuff, and the high schoolers, and on and on and on. Yes, a Satake diagram is obtained from a Dinkin diagram by blackening some vertices and connecting other vertices in pairs by arrows according to certain rules. What should you take first, topology or advanced linear algebra? Do you have to choose? Can you take them together? Yeah. Depends. I mean, those are it's hard to tell just from those words, right? Because the courses are very different. differ from institution to institution, and also even at the same institution, um, um, from instructor to instructor. But I mean, I feel like in some sense, advanced linear algebra is more fundamental and universal. But topology is cool and indispensable in its own right. Really, I would take them together. Heresy of talking about money in a math stream. Money, 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 money. Give me more money. YouTube ad revenue money. Tutoring student money. Hey, I'm participating in a program that prepares people to go to industry. So, which I wouldn't say it's guaranteed that that's what I'm going to do yet. My heart is still very much in mathematics, but I don't know. I like money. I want more money. Never really felt that way before, but then I got old in the last couple of years, and I started feeling like I wanted money. Oh wait, does this work? Wait a second. It says over a field such as the reals. I thought this was just a game we played for the reals. Maximal split torus. Take T to be maximal torus containing S. Over the separable algebraic closure. Then this has a Dinkin diagram with respect to some choice of positive roots. The Dinkin diagram has a natural action of the Galois group, and some of the simple roots vanish on S. Some of the simple roots vanish on S. What was S? It was a maximal split torus in G. Okay. And then you darken those ones. Is that what it is? The Satake tits diagram is given by the Dinkin diagram D together with the action of the Galois group with the simple roots vanishing colored black. Okay. I'm learning things in my own office hours. Is there a time we can talk about the transfer map and group cohomology? I could look it up. This is the thing. I know like the definitions of group cohomology, and I know that like the first cohomology group classifies the pure inner forms, and I know that somehow for the cases I'm interested in, I can reduce this to connected components of the center, and that's about all I need to know to make my research work. But transfer map group cohomology. So I probably should learn this more properly. But hey, you always have plan B, which is living like growth and Deacon his last years. Yeah, that's true. That's true. That's always an option. And no shade to you, but you're less famous and statistically speaking probably will be, which will make it a lot easier for you to disappear and not have people constantly come and harass you. So there's that. Trying to figure out what the transfer map looks like in this case. We got two groups. Following Weibel. A is a G module. The TR for transfer. Yeah, we could probably work this out. Probably work this out. Yeah, Falatrika, I see you sent a message, but then took it back. But I'm logging off right away. So if you want to re-ask your question before stream ends, I would try and do it soon. So my coffee's almost done, and I have a speaking of money, 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 money. I have a tutoring session. uh, Actually, you know what? I love tutoring not just because of the money that it brings, but I find it spiritually enriching. To be honest, I just love, I just love talking about math. To be honest, no worries. That's a shade only applicable to non-math people. How can you start liking math? Well, see, I'm not the right person to ask this question because I just do. I just like math, and I didn't have to make an effort to like it. I would say, well, first off, there's a couple things to say about this. Why do you want to like math? You know, I think obviously math can be a very useful thing, right? And so you know, you might want to enjoy it, say, for practical purposes, because if you enjoy it, it's easier to learn it, and then it's easier to apply those skills throughout your life. But there's also a part of me that thinks, well, you shouldn't try. Actually, is that true? I don't know. I was about to say you shouldn't try to like something, but that maybe that's not true. I do think I do think it's worth investigating a lot of different facets of life, and you know, spending time to try to get to like things, because I think a lot of things that people think they don't like is just a matter of familiarity. You know, if you don't like the taste of a certain food or something, just try eating that food every day for like a month, and you'll probably grow to like it. So, um, so I don't know. It's a complicated question because it depends on your background and where you're coming from, and where you want to go. So, I mean, the easiest way is to try and find a way to connect math to something that you care about. There's a lot of different math. So, like, I don't know, Google your interests and Google like mathematics of, and then type in your interest, and then maybe you'll find a link there that will motivate you. But yeah, on the other hand, I don't know. Like if you just don't like if you just don't like math, then you know, not everyone has to like everything. I think life is more interesting if you have a wide variety of tastes, but yeah, I mean, if that's just not your thing, if you know, you just really love gardening and you don't care about math, then I'm inclined to say just like lean into the gardening. Um, you know, wanting is already a bad motivation in general, but who are you to advise anyone? Yeah, who am I to advise anyone? It's interesting and you used to enjoy it, but sometimes the process gets overwhelming. Ah, philosophy major. I see. Yeah. Well, then there is so many cool things, so many cool places where you could connect with philosophy, right? I mean, basic logic can seem kind of dry, but there is so much cool stuff if you Google like math and philosophy. Um, yeah, I mean, I've mentioned on stream a couple times before. You know, there's these people have like formalized what Hegel. They've formalized Hegelian dialectics in category theory. There's this paper I've brought up also several times on stream from Ewodi, structuralism, invariance, and univalence. Like, go check out that. I think there's really cool things. Maybe this will be a little hard to read if your math background isn't strong, but check it out anyways, because I do think. Do you think there's? I mean, these are just tips of icebergs here. I mean, there's a whole ocean of giant icebergs. Computer science major, struggled with discrete math, but enjoyed topics like induction and combinatorics, which led you to switch to mathematics. Nice, nice. Yeah, that's how they get you. You get pulled in by these shiny, pretty objects, and then next thing you know, you're a math major. Hello, Super Baron, but also goodbye. I have a tutoring session in like 2 minutes, so I gotta go. I gotta log off. I hope everyone has a great day. You know, it's the start of a weekend. It's a beautiful day here. Uh, time to go prove some theorems. Hope you're amped up.
Made this be a bountiful weekend of proofs for you. So